Hey guys, so we're going to start chapter 6 today. We're going to do 6.1 first. In this one, we're going to be graphing again, but we're going to be graphing systems of equations. A system of equations is when you have two or more equations that are linked to each other, like this example right here. And the solution, right, is not like x equals 2 or whatever. The solution is an ordered pair that satisfies both of them. Now, there are three possibilities when we're solving these. You can have no solution, you can have one solution, or you can have an infinite number of solutions. There's no other possibility. Okay, so let's talk about each of them. The first one we call consistent. We say the system is consistent when the graphs intersect or they overlap. Another word for that is coincide. So when they intersect or they overlap, we say they are consistent. Okay? Now, there are two situations that happens. The first case is it's independent when there is exactly one solution. The second case, we call it dependent when it has infinite solutions. So let's take a look here at the bottom. So look at this first case right here. I have one line here. I have another line here. Those two lines, they intersect, right? They intersect. So they are consistent because they intersect. Okay? Now, how many points do they intersect at? Just one. So this has one solution. And this is consistent and independent. Okay, so we said to be consistent, they had to either intersect or overlap. Well, look at this one. This has one and actually another one that lies right on top of it. So because they do touch, they are independent. I'm sorry, because they do touch, they are consistent. But because they overlap, how many points do they touch at? An infinite number of them. So we say they are dependent. And this has infinitely many. Solution. Please don't say all real solutions because it's not all real numbers. It's only the solutions that are on the lines, but they're infinite. Okay? All right. So last one, inconsistent is when they are parallel, and so there is no solution because there is nowhere that they touch. So look at this one. That's one line. That's another line. They're never going to touch. So there's zero solutions, and they are inconsistent. Okay? So when they touch at all, they're consistent. When they don't touch, inconsistent. Okay, so let's go over here. Here we have a system of equations, and they're already graphed for us. What we have to do is we have to determine whether there is no solution, one solution, or infinitely many solutions. So this one, they don't touch at all, so there is no solution. You can either say that or you can say this. Okay, this one. So look at this one. We graph each one of them, and we graph it like y equals mx plus b, right? So look at this one. Look at the bottom one. Okay? The y-intercept is 2, and then we go up 1 over 3. So the y-intercept is 2, and then I go up 1 over 3. So that's this line, okay? This other one, okay, to graph it, I need to solve for y again. when I solve it for y, it's going to be 3x plus 2. Okay? So again, it's y-intercept is at the 2. You go up 3 over 1. That's how we graphed it. But regardless, these do intersect, so they have a solution, and they intersect at one point, so there's only one solution. Okay, so let's do this one. We're going to graph, and we're going to determine if there's a solution, and then we're going to name the solution. Okay, so for the first one, I'm going to graph this first one. The y-intercept is -2, so I go up 3 over 1, that's the slope, right? 3x minus 2. And for this one, you have to be super careful and use a ruler, because if you're off a little bit, the solution will be off as well. Okay? Now the next one, I'm going to graph that one in blue. The y-intercept is 1, and then I go down 2 over 1. Okay? Here we go. Okay, so do you see how they do intersect? This has one solution because they touch at one point, and the solution is this point right here, okay, which is 1/2, 0. Again, when you're using this, when you're doing this, use a sharpened pencil and use a ruler and make sure you are completely precise. Okay, this one. Let's graph the first one. Y-intercept is -1. And I'm going to go down 1 over 2. Okay, so let's see here. Oh my goodness. Okay. That won't work. Okay. The next one, I'm going to have to solve it for y. So I'm going to subtract x first. Okay. I'm going to get 2y is equal to -x minus 2. Let me rewrite that here. Okay, let's divide by 2. So what's y? -1 over 2x minus 1. Okay, so here, okay, I go down 1 over 2. Oh my gosh, look, it's the same exact line, right? So how many solutions does this have? Infinitely many. Okay, and I know some of you are thinking, well, can I just write I am? No. Okay, we're going to write infinitely many. The most you can abbreviate is maybe this. Okay? Okay, this one, the first one, y-intercept is 5. And then I go up 3 over 1. Okay, be careful with this one. It's tight. Okay, next one. I'm going to solve this for y. So this is going to be y equals 3x plus 4. Okay, y-intercept is 4. I go up 3 over 1. Look at how close these two are. And these are going to be parallel lines. Never going to touch, so it's no solution. Okay, let's take a look at these two equations though before we move on. The y-intercept for the first one was 5, for the second one was 4. The slope here is 3, the slope here is 3. Remember what we had talked about last semester. If two lines have the same slope, they are parallel. So that's another indication that we did that correctly. Okay, let's take a look at this one. I have one slope of 3 over 4, another slope of -3 over 4, not parallel. Okay? So let's graph the first one. The y-intercept is 7. And I'm going to go up 3 over 4. Please use a ruler. Okay, the second one, the y-intercept is 1. But now I'm going to go down 3 over 4. Okay, and then, you know what? I'm going to do another one. I just want to make another point. So here I went down 3 over 4. I can also go in the opposite direction and make another point, just so my line is totally precise, because this makes all the difference, right? If you're off a little bit, so will your solution. And so here we go. That's the solution now. And we can clearly see that that solution, first of all, there is one solution, and it's at -4, 4. Okay, a few things. This one solution is the number of solutions. The actual solution is this, and you have to have the solution as a coordinate. That means parentheses and comma. Otherwise, it will not be given full credit. Okay, let's do another one. The y-intercept for the first one is 8. I go down 1 over 1. So let's do this. Let me put a couple more points so it's precise. Okay. All right. The next one, the solution, the y-intercept is -7 all the way down here. And then I'm going to go up 4 over 1. Let's put another point. Over 1. 1, 2, 3, 4 over 1. Do you see that? When you do that, you already see that solution. So these lines intersect at one point. They are going to have one solution. And that solution, right, is going to have a coordinate point. So I do the format first. And the coordinate point is going to be 3, 5. Excellent. Okay, next. I'm going to solve this one for y. So first we're going to subtract x. It's going to be 2y is equal to -x plus 5. I suggest do that like on a scratch piece of paper, right? So you get everything right. Or do it like off to the side. Write everything down so you don't get it wrong. So what's that going to be? Y equals -1 over 2x plus 5 over 2. Okay. All right, so this one, 5 over 2 is 2.5. 1, 2.5. Especially with the halves, you have to be super careful. Now, we're going to go down 1 over 2. Okay? Down 1 over 2. Just over 2. Okay, so this is what it's going to look like. Oh, you see how I'm off of the marks a little bit? That might get me into trouble. Be careful. Okay, so this one, subtract 2x. I get 4y is equal to -2x plus 2. Divide by 4. Y equals -1 over 2x plus 1/2. Okay, so look at this one, right? The y-intercept is 1/2, but look, it has the same slope as the upper one. So we know these are going to be parallel. I'm going to go up 1, down 1 over 2. Okay? Isn't that cool? Right? So they're parallel. That means there is no solution. It's not enough to just show parallel lines. You have to also explicitly say there is no solution. Okay. So let's take a look at this one. In the xy plane below, the two lines intersect the origin. Which of the following pairs of equations can represent these lines where a and b are positive constants? Okay, so first of all, if they intersect at the origin, the y-intercept has to be 0. Okay, so already scanning this one has another y-intercept. It's not 0, so that doesn't work. Now, it says a and b are positive constants, right? If you look at this is positive ax, positive bx. So both of them have a positive slope. And what do we know about positive and negative slopes? If you have a positive slope, the line always increases. If you have a negative slope, the line will decrease. Well, in this case, the red line is decreasing, so it has a negative slope. The blue line is increasing, so it has a positive slope. So going here, if you look at the slopes, one has to be positive, one has to be negative. The only option is B. Okay. Each dot in the scatter plot below represents the temperature and number of people who visited the beach on 11 different days. The line of best fit for the data is also shown. The line of best fit for the data has a slope of approximately 57. Okay, so this is a scatter plot, right? So, this person, there was an average, when the average temperature was 27, this many people came. So that's like what? Like 120 people came when the average temperature was 29. This many people came when the average temperature was 33. This many people came when the average temperature was 31. This many people came. When you draw these points, okay, they don't all align on one line. So what we do is we try to approximate the one line that fits this data the most. That is called the line of best fit. And you see how that line goes through the middle of all of the points, okay? Now, that line has a slope of approximately 57. So it says here, according to the line of best fit, what is the number of people rounded to the nearest 10 predicted to visit this beach on a day when the average temperature is 32 degrees? So 32 degrees, that's right here. Okay, when I go up, this is where I hit the point, the line. Okay, so now we have to see how many people are expected to visit the beach on that day. And if I follow this here, it's 480 people. Okay. According to this estimate, how many additional people per day are predicted to visit the beach for each 5-degree increase in average temperature? Okay, well, if we go 5 degrees below, okay, where would 5 degrees below be? 5 degrees below 32 is 27. So let's go to 27. Where does that go? In the middle here. What's between 160 and 240? 200, right? Okay, so it says how many additional people a day are predicted to visit if there's a 5-degree difference. So basically we want to know how many additional people are going in between these two temperatures. Well, that's going to be 480 minus 200. That's 280 people. Okay, so that's it for today, and then the homework is on the lesson plan, and it's going to be due next class.